Okay. So I'll be sharing my screen. Okay. Hello everybody. I hope I'm audible now. I did change my network connection also. This will be a continuation to your neurobiology course, and let me just begin with it. I am Arveen Kaur for the people who are joining this week onwards. I am a PhD scholar at Department of Biological Sciences and Bioengineering at IIT Kanpur. And what we'll be doing in these sessions is that it is kind of like a revision session for you guys for the course Neurobiology. First, what we'll discuss is the previous year's questions that were given in the previous years as the previous year's assessment for week 3. And we'll discuss their answers. And then we'll do a quick recap of what has been taught to you in this particular week, right? It will be a revision of sorts. And if you have any doubt in any concept, then you can speak up and maybe I can help you out through that. Right. Yeah, just a moment. Let me just begin with this. I hope my screen is visible. I just so let's go on to the first question for this week. So the first question is a relatively simple one. It has like you guys might even have studied this in biochemistry or some other subject, if not over here for the first time. The question is hydration shell of potassium ion is smaller than the hydration shell of sodium ion. Is this statement true or false? This in with this week's lectures, you might have gone through. Sir has explained how there are a specificity of various channels for various ions. And during the explanation of that concept, he basically taught how, like, what is this hydration shell? How is it relevant in that matter, right? So we have seen over there, we have studied that potassium, although the size of the potassium ion by itself is bigger than the sodium ion, but because of this bigger size, the you know it is not very concentrated. The charge that it is hold with which it is holding the oxygen ion surrounding it is not very concentrated, due to which instead of potassium, sodium actually has a larger hydration shell. Right, so that is what is explained to you in this figure also. So potassium has the same amount of charge as sodium, but over a larger volume, right? So its charge density is lower, right? So if the area that it covers is more, the charge is not as densely packed, right? So that is why over here in sodium, you can see although the ion is smaller, it can basically have more localized charge and it attracts more water molecules in that regard, as compared to potassium that has a larger uh, and as compared to potassium, it does have a larger potassium hydration shell, right? So coming on to question number 2, it says in a current clamp, we measure the current by controlling the voltage. Is it true or false? Okay. So this statement is false, right? Why is it false is how when do we measure current? It is another technique. It is known as voltage clamp, right? So clamping anything thing means holding it steady, right? So in a current clamp, we will hold the current steady and we will assess the other variable, which is voltage. In a voltage clamp, we are holding the voltage steady and we are assessing the other variable, that is the current, right? So in a current clamp, we are not measuring current. Instead, we are measuring voltage, right? Then we have another question which is related to the previous one. This is regarding voltage clamp, right? So in a voltage clamp, the compensatory current is positive when the net ionic current is flowing out of the neuron, right? So is this true or is this false? So this statement again is true, right? So why is it true? Because if we are saying that the ionic current is flowing out of the neuron, right? So it is in a positive direction. It is flowing from a direction, a place of a negative charge to positive charge, right? Which means that the electrons will be flowing in the opposite direction, right? So if the net ionic current is flowing out, then what will have to be done? We have to basically inject positive current into the cell to maintain the desired voltage, right? So that is what is going to be done. So you might recall this setup of a voltage clamp, right? From this, what happens is over here we'll focus on a few key components and we'll go through the entire thing again when we are doing the recap, right? So what is happening is that we basically have an electrode in the membrane, right? This electrode is giving us a reading of the membrane potential over here, right? And over here, we have one command potential that we have set. So this membrane potential is the reading of what is the membrane potential currently, and the command potential is the amount of potential that we actually desire the membrane potential to be retained at, right? So if, for example, this membrane potential is at a value x and the command potential is at a value y, right? So this feedback amplifier will judge that they are both not at the same level, and it will, subtract maybe y from x, and whatever the amount is, right? If it is positive, it will give the current into the axon, and if it is negative, it will take current out of the axon, right? So the flow of current will change, but there will be some kind of a compensatory current that will be going in or out, such that the command potential is equal to the membrane potential, right? So maybe in this case, the current is actually going in, right? And that is equating the membrane potential, at least for that very time point, to the command potential. So now this is also y and command potential is also y. Okay, so the feedback amplifier will have no difference, right? So it will not send or receive any current from this particular axon, right? So that is how this experiment is actually running. So if basically the ionic current is flowing out, the positive current will have to flow in to compensate for that, right? So the compensatory current will always be opposite of what is flowing out of the membrane, right? Coming to question number 4. Which of the following is true about the structure of an electrical synapse? A pore is made of a small protein chain that passes through both the neurons? Or is it a pore made of 6 protein chains, all of which pass through both neurons? Or is it a pore made of 12 protein chains, 6 of which pass through each neurons? Or is it a pore made of 24 chains, 12 of which pass through each neuron? Right? So which one of these is the correct statement? So you can take a little time, go through the statements and the question, and we'll come to the answer shortly. Okay, so the correct answer over here is option number C, right? Why is it option number C? Because over here, as you can see, you might recall the concept of these connexons, right? So these connexons are basically the protein channels that are there, right? Which are going to transmit the electrical synapse across the membranes, right? In case of a synapse, we have two membranes, right? One is the membrane of the first neuron that is sending the signal, and the second is the membrane of the second neuron that is receiving the signal, right? So there is one connexon in each membrane, right? As you can see over here, which includes six protein channels or connexons, right? Overall, we have 12 protein chains when taking into account two membranes, right? So we are taking into account both neuron one, the membrane of neuron one, as well as the membrane of neuron two. Okay, there is some. I'll just share my screen again, okay? Yeah, so as we were saying, there are two sets of connexons that are present. One will be in the first neuron that is sending the signal, the other will be in the second neuron that is receiving the signal. Each connexon has six connexons or six proteins each, right? And one connexon is present on one membrane and the other is present on the other membrane, right? And they are basically connecting these two membranes because there is a pore in between them through which the signal is going to pass, right? So once they sit on one another, there will be a long, this tube, junction that will be achieved, which will help in transfer of the signal, right? So each connexon, like the sum of both connexons will have 12 protein chains or 12 connexons, and but one membrane will only have, or each per neuron, we will only have six of these connexons, right? Okay. So which of the following channels can become inactivated? Okay. Is it the passive sodium channels or the passive potassium channels or voltage gated sodium channels or voltage gated potassium channels? So which of these channels is actually capable of becoming inactivated? Okay. Yeah. So the channel that can actually become inactivated is the voltage gated sodium channel, right? So why do we say that? Because the passive channels are the channels that are already open, right? They are the leakage channels. So they will always remain open. And when we were studying about the membrane potential, we have also seen that the voltage gated potassium channels do not go into an inactive state, right? That is why that after hyperpolarization actually happens, because they never do get inactivated. But the sodium voltage gated sodium channels can get inactivated, right? So this is the answer for that. Then we come to question number 6, which is a small depolarization can fail to generate an action potential because the leakage currents dominate over the voltage gated sodium channels, or voltage gated sodium currents dominate over the leakage currents, or voltage gated potassium currents are absent, or leakage currents are absent, or voltage gated sodium currents are hyperpolarizing. So you can go through the options once. Thereafter, I'll discuss the answer. So the answer for this one is option A. That is, the leakage currents will dominate over the voltage gated sodium channels. Right? Why? Why do we say that? Because we were seeing like not all intensities or all magnitudes of currents were actually, uh, you know, attaining a threshold that could actually generate a action potential, right? So if there was a small depolarization, that is, if there was a small positive current, then what was happening is, how was it different than the current that was actually able to generate action potential is that in that case, enough sodium channels were not actually activated, right? Once the sodium channels are enough sodium channels are activated, what they do is they activate even more sodium channels in their vicinity, right? So there is a amplification of that signal, thus we obtain a very distinct peak in case of an action potential. But in if positive current is failing to generate an action potential, it is because the cumulative effect of sodium ions, voltage gated sodium channels, is actually overcome by the effect of the leakage currents, right? And what are these leakage currents doing? It was actually sending the chloride ions, the uh, more of the positive charge inside, right? So more and more sodium and potassium were actually coming inside, and it was sending more of the negative charge outside, right? So that is what these leakage currents were doing, and some of them that were not electrically, managing this, but concentration based, they were managing. So they were trying to send the potassium ions outside and the sodium ions inside again, right? So what they were actually disrupting the peak that the cumulative effect of sodium channel activation might have had, right? So that is why they are failing to generate an action potential. So the action potential requires voltage gated sodium channels, which increase the membrane potential to be larger than the leaky currents, which are actually decreasing the membrane potential, right? Because the equilibrium, what will these leakage channels do? They will work as far as the equilibrium potential of the particular ion is not reached, right? So, for example, the equilibrium potential of sodium is in a positive value, right? So, it will keep sending the sodium outside until it has achieved that equilibrium potential, right? Similarly, the equilibrium potential for potassium is has a more negative value, right? It is around -75. So it will keep sending the potassium ions inside, right? So that is how it is going to work. And because no two different ions equilibrium potential can actually be attained successfully, that is why it is an ongoing process, right? So leakage currents are always going to be present. Yeah. So question number 7 is, which of the following is true during the relative refractory period, right? Is it that the action potential is not possible at all, or the action potential is possible but with a larger than usual stimulus, or the action potential is possible with a smaller than usual stimulus, or the action potential is inverted, that is, it is hyperpolarizing, or it will cause more negative effect? Sorry. So which one of these are true? So this is actually a good question. It is going to test the logical reasoning behind this concept, right? Okay, so I'll take a little while to explain this one, I think. What will happen in this case is that during the relative refractory period, action potential is possible to be generated, right? When is it not possible to be generated? During the absolute refractory period. At that time, it can definitely not be generated. But during relative refractory period, it is still possible, right? So we need to understand the mechanism behind it to actually answer it correctly. what does it say? In the relative refractory period, some of the voltage-gated sodium channels are inactive. So a larger stimulus is needed to open sufficient number of channels to generate an action potential. Right? So you might remember um, this kind of a chart, right? Wherein earlier this, okay, I will face a problem with the drawing over here. So let us ignore the first line that I drew, right? And let us say that the second line that I have drawn was the initial threshold for the action potential, right? After this, there was an action potential that had arisen, right? And then it would have gone down. In case of action potential, you can ignore the coordinates that I have drawn, right? The XY coordinate that can be ignored for now, right? And what they are saying that initially this much threshold was okay to basically stimulate this action potential, right? Now it will go into a refractory period after a while, right? Over here, it is actually in the action potential only, right? Now this phase before it starts rising is the refractory period, right? Still here. Now, one part of this refractory period is the absolute refractory period, right? This first part is the absolute refractory period, and this other or the larger part of this refractory period is the relative refractory period, right? Now, what will happen in the absolute refractory period? That means that all these voltage gated sodium channels that are there in that vicinity are closed, right? Definitely any amount of stimulus cannot generate another action potential. But in the this relative refractory period, what is happening, the second part is that if like a larger amount of stimulus is given, larger than the previous threshold, like if it is equal to this threshold only, it will not generate an action potential. But if it is larger, say this much, right, then it can generate another action potential over here, right? Okay. If it was like as the time progresses, a smaller amount of current can also generate an action potential. But the smaller amount of current can never go below the threshold, right? This much can never generate an action potential. It should always be at least till the threshold value, right? And that threshold value will be able to generate an action potential after this refractory period is over, right? Now, why a larger amount of current will be able to stimulate it in the relative refractory period is because as the time passes, a few sodium voltage gated sodium channels will start becoming active again, right? So its inactive state will be lost. It will just come into a closed state, not even active, it will just come into a closed state. So if enough current is given, they can be activated, right? And as many number of sodium ions can actually be activated, again they have that capability of activating other sodium ions in their other sodium channels in their vicinity. That is why a higher current can actually stimulate an action potential, right? So B is the answer over here. Yeah. Question number 8. If myelination is removed from an axon, which of the following is most likely to happen? Will the conduction of action potentials become faster, or the conduction of action potentials will become slower, or the conduction of action potentials will become more energy efficient, or the conduction of action potentials will occur at the same speed? So which one of these will happen if the myelination is removed? Right. So for this, you need to recall what is myelination. Myelination is like a kind of insulation that is present on the axon of the neuron, right? So the answer for this one is that it is going to become slower, right? So usually what is the ideal case scenario when we are transmitting an action potential, that it will be conducting without any deterioration in the action potential, right? So, but if that can happen over long distances if there is some kind of an insulation or there is lesser resistance that is present within the axon, right? So this lesser resistance in the case of the squids comes with its giant squid axon, which has a very large diameter, due to which obviously the resistance is decreased and the conduction can occur flawlessly, without slowing. But in case of humans, since the diameter of our axons is not very big, what was the modification that was made in us or in our anatomy and physiology was that there was a insulating layer which is known as myelination. And this myelin sheath is basically secreted by the oligodendrocytes that we had studied about when we were looking at macroglia in the first module, right? So those macroglia, known as oligodendrocytes, release this myelin sheath, which basically goes and forms an insulation over the axon. And due to this insulation that is formed, it basically increases the membrane resistance. When it increases the membrane resistance, it makes it difficult for the ions to cross the membrane, right? So thus, since they will not be able to cross the membrane, they will keep moving forward, right? So that helps in increasing the speed of conduction, right? But if we remove myelination, it will obviously make the conduction slower, right? Because there will be the passage of these ions that will be into and out of the membrane at each point in the axon. Okay. So coming to question number 9. The synaptic delay is smaller in chemical synapses than in electrical synapses. Is it true or is it false? So I believe at the beginning of this module, we had studied that the electrical synapses or the electrical gradient, both cases, it is the faster one, right? The chemical synapses is much slower than the electrical synapse, and the chemical gradient also changes much slower as compared to the electrical gradient, right? So this statement is false, because the electrical synapses will be faster due to direct conduction of ions from one neuron to another. Right over there, what was happening is that those two protein channels, the connexons, were coming and meeting, and there was direct transfer of conduction of these action potentials from the first neuron to the second neuron. In the chemical synapses, however, there had to be neurotransmitters that had to be formed in the first neuron. These had to come and basically attach to the membrane of that first neuron, get released into the junction between the two neurons, and over from there they had to go bind to the receptors. Then only after that binding, only the conduction of that signal would occur in the second neuron, right? And then again, there had to be a change, from the chemical signal that it is getting. It had to be transmitted into an electrical signal to go through that neuron, then again into a chemical signal to go through the synapse. So that is a time-taking process, right? So hence, this statement is false. Coming to question number 10. The smaller stimulus will result in a smaller action potential in a typical neuron. Is it true or false? So this statement again is false, right? Because the action potential will never change whether it is after it has gone through a threshold. The peak of an action potential will not alter, right? So this size of action potential does not depend on the size of the stimulus. Rather, it will depend on the status of the voltage gated channels, right? So what will happen is, if the stimulus is smaller than the threshold, right? Smaller than the stimulus that can actually make that depolarization go up to a threshold, then it will not produce a action potential at all. If it is reaching that threshold, it will produce an action potential. And even if it is surpassing that threshold, it will still produce the similar peak of an action potential. It will not produce a higher or lower peak, right? So it is not depending on the size of the stimulus. It will depend on like whether the voltage gated sodium ions channels are activated, deactivated. Similar is the case for the voltage gated potassium channels, right? So that is it for the assessment part, the previous year questions part. We'll come to the recap of what has been taught to you. And okay, I'll just share that screen. Yeah. Yes. So as I had explained in the last session also, um, we had basically studied up till the length constant, up till the in the second module we had discussed up till the length constant and how these time and length constants are actually determining how the conduction is happening and how it can be affected, the factors that it depends upon. These were the two major ones, right? So yeah, so we'll pick up after that from the Nernst and the GHK equations and study about the equilibrium and the membrane potentials. And last time also we did talk about action potential, but we did not really ponder upon what it exactly is. Right, that is what we'll be clarifying in this particular discussion session. So I'll just take a short break and we'll begin. Okay, so I think I'll share my screen again. Um, yeah. So where we'll begin is the driving forces of of the concentration and the electrical gradients. Like what are the driving forces? We have talked about it briefly, that the ions will be the driving forces in this case, right? So we are going to talk about how they will basically decide which way the current is going to flow, or what is going to be the value of the membrane potential, how is it going to be determined, right? That is going to be the first part of discussion today. So, uh, both the electrical and concentration gradients are going to be the driving forces, which will result in the value of the membrane potential, basically, right? And we can see from this figure over here that the direction of concentration gradient and electrical gradient might not be the same, right? They might be in opposite directions based on which particular ion we are talking about, right? Why are we saying that? Because, for instance, if we take chamber B to be the inside of the cell, or the intracellular or the cytosolic side, and chamber A to be the outside or the extracellular side, we can see that inside, uh, although due to the presence of a lot of anions over here, which is the chloride ion, there is more negative charge, right? But there is also more amount of potassium that is
I'm unable
present
to hear you.
inside. Oh, okay. I am unmuted. Okay, I'll just share my screen again, maybe. Okay. I hope I'm audible now. Am I audible?
Ma'am, we cannot hear you.
Still can't hear me? Okay. Um, okay, I'll just join again. Okay, am I audible now? Um, Audible?
Yes, audible. Still.
Okay, okay. So I'll just share my screen again. Okay. Okay, I do not know like since when I was not audible, so I will go through this first slide again because that is all we talked about in this recap session till now. What I was saying is that the driving forces are going to be the two main forces that are going to drive the movement of ions into and out of the neuron are going to be the electrical gradient and the concentration gradient, right? And these two cumulatively will be the determinants of what the membrane potential is actually going to be, right? And as you can see from this particular figure, you can also make out that it is not always going to be the case that the concentration and electrical gradient will be uh, going on the same side, right? It might oppose one another at times, right? For example, over here, if we take an example of chamber A as the extracellular side of the neuron and chamber B as the intracellular or the cytosolic side of the neuron, and we see that chamber B has more negative charge and chamber A has more positive charge, right? Despite having more positive charge over here, when we look at the potassium ions or the positive ions that we are actually going to focus on over here, we can see that more amount of these potassium ions are present actually in the cytosolic side than the extracellular side, right? So because the electrical gradient wants more of these potassium ions inside, right? That is going to push them further in, right? Why? Because inside the overall charge is negative, right? Outside the overall charge is positive. So the positive charge will flow from its higher charge to its lower charge area, right? So this positive charge will be flushed inward, and the uh, chloride will be flushed outwards when we talk about the electrical gradient. That is what it will try to do, right? But when we come to the concentration gradient, we can see that the amount of potassium ions outside is lesser than the amount of potassium inside, right? So the concentration gradient will try to send these potassium ions outside, right? Similarly, it will also try to send these chloride ions outside, right? So over here, the concentration gradient and electrical gradient for potassium will be opposing, but that for chloride will actually match, right? Because both the electrical gradient and the concentration gradient, both of them are going to try and send these chloride ions outside into chamber A, right? That is the extracellular chamber. So it may or may not oppose one another, the two gradients, concentration and electrical gradient, right? So we'll move on and we'll first talk about the concentration gradient in detail, right? Again, we'll focus on these potassium ions initially. And like we talked, the amount of potassium ions or the concentration of these ions is going to be more inside the neurons than outside the neuron, right? So naturally, their flow will be towards outside when we talk about the concentration gradient, right? So if we'll open the potassium channels, the ions will be allowed to flow outside, right? And there will be energy released during this process because it is an energetically favorable action that it is doing, right? This energy can be written as RT, wherein R is a constant, T is the temperature at that time, then natural log Ki upon Ko. That is concentration of potassium inside upon concentration of potassium outside, right? And if this ratio is more than 1, That is, if the ratio is higher inside than outside, then the ratio will actually be positive, and positive energy will be released when potassium ions move outside. So it will actually release energy, right? On the contrary, if we talk about electrical gradient, right? So over here, we say that outside the electrical gradient is 0 volts and inside it is E volts, right? E volts can be considered as less than zero, because we know that the membrane potential for neurons is negative, right? So this E will be in a negative, having a negative value, right? So the natural flow of potassium with respect to its electrical gradient will be inwards, right? So the energy released per mole for the inward movement will be minus ZEF, wherein Z will be the charge of the ion, which over here is going to be +1. Right? Faraday's constant is this F value, and E is the membrane potential, right? For example, a membrane potential can be minus 70, right? So the energy released per mole for outward movement will be ZEF, right? So inward movement, the energy being released has a minus sign. If we are throwing the same thing outside, it will be like the symbol will be reversed. That is why we have written it as ZEF instead of minus ZEF. Why? Because potassium ions are positively charged and they will be attracted towards the negative potential, right? That is inside the cell. Although the concentration gradient was driving these potassium ions from the inside to the outside, the electrical gradient will be trying to bring the potassiums inside, right? So if we say that at equilibrium, the net energy change is zero. So what is equilibrium? It is a value wherein there is no energy change. Nothing is going to go into or out of the membrane. Or even if it is going to go, say that two potassium ions moved out of the membrane and two potassium ions moved into the membrane. So the net change is zero, right? So the value, the equation will look something like this. That is ZEF plus RT ln Ki by Ko is equals to 0. Right? So this is a net energy change and it will be equal to 0. Now we know what these variables are. We know that Z is the charge, E is the potential that is present, the voltage that is present inside, right? F is the Faraday's constant, R is again the constant, T is the temperature, Ki is a value of potassium or concentration of potassium inside and concentration of potassium outside, right? So in general, for any ion X, right, even if we don't consider potassium ion per se, we can take any ion X. This will be the Nernst equation. It will be given by rearranging this particular equation, and it will, look something like this, that E for that particular ion is going to be RT by ZF, natural log, XO by XI. Right, so this is known as the Nernst equation, and it was first derived by Walter Nernst in 1888. And this has been very useful, right? We are going to use it multiple times in this very lecture to basically determine what the equilibrium potential for individual ions are going to be, right? So over here, R is a constant value. It is the gas constant. This is the value that it has. T can be any temperature. Generally, it is taken as the room temperature that we will see in the upcoming slide. Faraday's constant has this value. Z is the valency of the ion, and XO is outside concentration. XI is the inside concentration. Right? EX is basically known as either the Nernst potential or the reversal potential or the equilibrium potential of the ion X. Right? So we can also derive this Nernst equation to fit for room temperature cases or events, which are the most common ones. And we can say, so, and we can say that at room temperature, if we say that T is equals to 25 degrees Celsius or 298 Kelvin, then RT by F will approximately be equal to 25 millivolt. right? So this equation will look something like this, wherein natural log will be changed by log base 10, and it will look like this, that Ex, or the Nernst potential for ion X, will be equal to 58 millivolt upon Z, or the charge of that ion, into log of XO upon Xi. That is its concentration outside versus its concentration inside, right? The log base of that. So now we can try the Nernst equation for potassium ions in the squid giant axon, right? We have already seen that in the squid giant axon, what is the concentration of potassium in the cytoplasm? It is around 400, and concentration of potassium in extracellular fluid is around 20, right? When this is the case, and we put these values into this equation to derive the Nernst potential, we find that the Nernst potential is equal to minus 75 millivolt, right? Also, at minus 75 millivolt, the electrical gradient and the chemical gradient for K plus ions will be balanced out, right? So if the value of the membrane potential will be equal to minus 75, then outside versus inside, there will be no net exchange of sodium of these potassium ions, right? It will be balanced out. Then the equilibrium potential for potassium ions is minus 75, as is shown in this representation also. If the membrane potential is equal to the value, then there is no net movement of potassium ions, because the electrical gradient and concentration gradient will balance out, like we just talked in the previous slide, right? But what will happen if the membrane potential goes below minus 75 millivolt, right? So if it goes further below this, what will happen? The electrical gradient will become stronger, right? If it goes further below this value, electrical gradient will become more stronger, and it will try to push more uh, potassium ions inside, right? Which will basically bring the brain potential back to minus 75, right? So if, for example, this value goes from minus 75 to minus 85, it will become more negative. What will the electric potential do? It will attract more potassium ions from outside, right? More positive ions. As there is more flow of positive ions inside, again, it will come back to a value that is the normal baseline value for potassium, that is around 75 millivolt, right? That is going to happen. What is going to happen, right? On the contrary, what will happen if the membrane potential will go above minus 75 millivolt, right? So if it goes to less negative than this, maybe minus 60 millivolt, right? Then what will happen? Then instead of the electrical gradient, the concentration gradient will play a stronger role, right? The electrical gradient will become weaker. Why? Because now it is going towards a more positive direction. It is what is happening due to the electrical gradient, right? Now the chemical gradient will become stronger, and it will push some K plus ions outside, which will help bring the membrane potential closer to minus 75 millivolt, right? So that is going to happen. So the concentration gradient will change more slowly as compared to the electrical gradient, right? As we just talked, in case of synapses also, the chemical synapses will be slower than the electrical synapses. So electricity is one of the fastest modes, right? So that is going to occur in the order of milliseconds maybe, and concentration gradient is going to change much more slowly, right? So let us now look at the electrical representation of a single potassium channel when we are considering that it does not have a concentration gradient at all, right? So it is an unusual assumption to make, because in general, in an actual living axon or an actual living neuron, it is definitely going to have a concentration gradient as well. But over here, we are considering the representation, or looking after the representation, as if it did not have a concentration gradient, right? In the absence of this concentration gradient, the K value, or the Nernst potential, will become zero, right? Because there is nothing to equate to, right? There is only the electrical gradient that is remaining. It does not have to equate to or compete with anything. So the Nernst potential will be zero, right? And this is the uh, what the membrane will look like, right? So this is the outer side of the membrane, the inner side of the membrane, and gamma over here will be giving the conductance of the membrane. That is how much potassium can actually pass through this membrane, right? Which will be the opposite of, or one inverse of the resistance of this membrane, right? So that will be the conductance of this ion channel, right? Now, if we derive Ohm's law in this situation, what will it look like? One, I usually Ohm's law is current is equals to voltage divided by resistance, right? Over here, since 1 upon resistance is written as gamma, we can write uh, I, or current, you will be equal to conductance into voltage difference, right? And the slope will look like this, wherein it will pass through this point zero, right? And the slope will of this particular graph of I against V, current against the voltage, will actually give the conductance, right? But actually, in presence of a concentration gradient, what is going to happen? Over here, the Nernst potential will not be equal to zero. There will be no ionic current when the voltage is equal to the Nernst potential, right? Why? Because if it is actually equal to the Nernst potential, then it means that there is no net exchange of the ions, the potassium ions, and the electrical and concentration gradient have actually attained or have actually balanced out, right? But if V is not equal to the Nernst potential, there will be current flowing through the channel, right? And this will push V towards the EK, right? So this will try to push V, that is the membrane potential over here, towards the equilibrium potential of the potassium, right? So this is what the slope will look like. It will not go through the center. It the conductance over here will actually give what is a amount of conductance of this particular ion that we have in a case where a concentration gradient is present along with an electrical gradient, right? V above or below EK or Nernst potential will result in potassium current, right? With the same IV slope as before. The slope looks similar. The coordinates for the slope have been changed, right? So over here, the current for the flow of potassium ions is going to be equal to the conductance of the flow of potassium ions into Vm, that is membrane potential, minus Ek, that is equilibrium potential of this potassium ion, right? So V minus Ek is going to be be multiplied into the conductance, and that will give the amount of current that is passing through, right? So this is what it will actually look like. Wherein in this example, Ek, or the Nernst potential for potassium ions, can be represented by a battery, right? And this battery, as you can see, have different charges, right? So it has more negative charge inside and more positive charge outside, right? And it is connected in series to the conductance or the resistance, right? Now, instead of a single ion channels, there are actually multiple potassium ion channels that are present in the membrane, right? So all these multiple potassium ion channels will go in series, and they will have the value K, that is the number of potassium channels present in the membrane, into the conductance of these potassium ion channels, right? So this is what it will look like, right? And this will give the value IK is equals to GK into V minus EK, right? Where EK does not depend on the number of the potassium channels, right? Because equilibrium constant for potassium is going to be the same, whether it is in one part of the membrane or in a very different part of the same membrane, right? EK is not going to vary. The number and the conductance might vary, right? So if we look at a simplistic diagram for this one, we can see that if these two are the two sides of the membrane, the cytoplasmic side and the extracellular side, there is capacitance or insulation of charge between these two membranes, which is represented over here. And there is also some amount of conductance that is there between for a particular ion between these membranes, and the equilibrium potential is depicted as EK, or this battery that is connected in series with the conductance over here, right? So different ions will actually have different equilibrium potentials. Till now, what we have talked about is the potassium ions, right, that have the equilibrium potential as minus 75. Now, if we take the value of the sodium ion channels and put it in the Nernst equation, right, in that equation wherein that minus 56 upon minus 58 upon that uh, upon Z into the natural log of the concentration outside upon concentration inside, it is going to give a different value. So is the chloride ion, right? So the value of equilibrium potential when put into Nernst equation for sodium ions will be plus 55, and that for chloride ions will be minus 60, right? So this is going to be the actual diagrammatic representation of this as the circuit that we were talking about previously, right? Also over here, you can see that the batteries for sodium, potassium, and chlorine have differing, you know, sides or different charge as expected from the different values of equilibrium potential, right? So both potassium and chloride have a negative equilibrium potential, wherein this negative potential arises from within the membrane. That is why their negative potential is towards the inside and positive is towards the outside, which is vice versa for the sodium potential, right? Sodium ion potential. So the equivalent circuit for this is going to look like this. The individual conductances along with the individual batteries are going to be shown like this. They are going to be connected in parallel to one another, while the batteries are connected with series in with the conductances. There is going to be the capacitance that is present within the between the cytoplasmic and extracellular side of these membranes, right? So this is what it will look like. Also, in this figure, E denotes only the magnitude of the Nernst potential, right? It is not going to denote the symbol or sign, anything like that, only the magnitude of the Nernst potential. So the K plus ions would try to take the membrane potential close to minus 75 millivolt. The sodium ions will try to take it close to plus 55 millivolt, while the chlorine ions will try to take it to minus 60 millivolts, right? So every ion is competing to actually achieve a membrane potential that is equal to their own equilibrium potential, right? So there is a competition that is continuously going on. So what will actually determine the final membrane potential in neurons? Usually at rest, there will be more potassium ions which will be open than the sodium ion channels, right? So because more potassium channels are open, obviously that will have a more larger say in what the membrane potential is going to be, and we are going to discuss that further, right? So let's consider the case when only K plus channels are initially open, right? So when this happens, then the voltage will be equivalent to the potential, the Nernst potential for the potassium ions, right? But then what will happen is a few sodium ions will also, sodium channels will also start opening. Sorry. Once this happens, this is what it looks like, right? Initially, let us consider only potassium channels are open, right? So the chemical gradient is actually driving the potassium outside while the electrical gradient is driving it inside, right? Because the concentration is more inside and less outside, concentration, chemical gradient is taking it in the direction of its concentration gradient, right? And electrical gradient is pushing it inside because there is more requirement of a positive charge inside the membrane than outside the membrane, right? So the net current or net driving force over here will be zero, right? Then see that the potassium and the sodium, both the channels open, right? So these three were depicting the potassium channels, and we talked about this, that more potassium channels are actually open than the number of sodium channels. When the sodium channels actually start opening, what will happen is that since it is a positive ion, right, it will be driven inside by the electrical gradient because more amount of positive charge is required inside the membrane because it has a negative value, and because its concentration is also more outside than inside, via the chemical gradient also it will be pushed inside, right? So these will, the net driving force will be towards the inside, right? And the next net current will also be towards inside, right? Thereafter what will happen is that transiently a steady state will be reached, right? In the steady state, the potassium ions will also try to, reach their equilibrium potential, and so will the sodium ions, right? So the net driving force of the potassium ion is going to be outside in both the cases, and is going to be outside, and the net current is also going to go outward, right? And the net driving force of sodium is going to be inside, and the net current will also be inside. Once these currents actually cross each other and there is no net current that is flowing into or outside the cell, that is when we call it as a steady state over here, right? And this is what it is going to look like. At steady state, Vm is between Ek and Ena, right? So Vm is going to be between Ek and Ena, right? And it is going to be somewhere around here. So we know the value of Ek is around minus 75 millivolts, En is around minus plus 55 millivolt, right? So what will happen as the time passes, because of the flow of sodium ions inside and some potassium ions outside also, what will happen is that the voltage will actually start increasing or depolarizing, right? So it will go towards a positive value, but after a time, it will not be able to surpass a particular value because there is also exchange of potassium ions that are being driven inside due to the electrical gradient, right? So a steady state will be reached wherein there is no net current that is being transferred, and such a plateau will be obtained, and this will be the resting membrane potential, right? So note that the steady state or VR, at this particular steady state, the K plus ions are continuously still trying to reach minus 75, so they are moving out. The Ne plus ions are continuously trying to reach plus 55, so they are continuously moving in. If the K plus and Na plus currents balance out, the membrane potential stays at VR or resting membrane potential, right? Or the steady state. So if we use an equivalent circuit to determine the resting membrane potential, what is it going to look like? It will look something like this, right? So over here, we are not actually denoting a symbols over here, but there are conductances of Na, K and Cl that are basically drawn along with their batteries, or which are depicting their nernst potential or equilibrium potential. And okay, these are in parallel to one another and in parallel to the capacitance between the inner side and the outer side of these membranes, right? So this is what it will look like. At steady state, there will be no change in the voltage. The net current flowing out of the membrane should be zero. Thus, V minus ENA into the conductance of Na plus V minus EK into conductance of K, and V minus ECl into the conductance of GCl is going to be equal to zero. This will give the membrane potential value, that is Vm, as ENA into GNA plus EK into GK plus ECl into GCl upon the conductances of NaK and Cl summed up, right? So this is actually going to be a kind of average value, right? But it is not, and it is going to come out to be minus 69 millivolt in this case, right? But the important thing to note is that it is not simply an average of the three values, right? But it is actually a weighted average. It is weighted by the conductance. So if the conductance of potassium is higher, then the final voltage will be closer to the potassium's equilibrium membrane, right? We know that the conductance of potassium is highest in the resting state, right? Because more of the potassium ion channels are open than the sodium or the chloride ion channels. Therefore, it is not surprising that the value comes closer to the equilibrium potential of the membrane, right? Now, this is a more simplistic representation of the resting membrane, wherein the conductances are summed up and the value of ER is taken as a weighted average over here, right, which will be the equilibrium potential of these various ions, right? Then these passive channels together that are basically driving the ions into and outside the membrane as in accordance with their electrical and concentration gradients are basically going to be known as the leakage channels, right? So they are also passive channels. That is that they are not utilizing energy to do any of these processes, right? So there is still one thing that we are missing out, that not all the current flow or exchange of ions is actually occurring through the passive process, right? There is also an active process that is involved. So we have basically assumed that if sodium, potassium, or chloride currents balance out, the membrane potential stays at the resting membrane potential. But this is actually not true, right? It cannot go on indefinitely because the concentration gradients will deplete, right? As the sodium ions are moving inside, there will be a point, if they keep moving inside, then there will be more of sodium ions inside than outside, right? Similar for potassium. Initially, yes, we do know that potassium ions are more inside the membrane, but eventually there will come a time where, since they have been moving out of the membrane, there will come a point wherein they are more abundant outside than inside, right? So, sorry. So the concentration gradients are maintained in parallel by the active transporters, right? So what are going to be these active transporters? They are going to be the pumps, or one of the most common pumps that we have already discussed and studied about is the sodium potassium pump, which have non-zero net currents, right? Why does it say it has non-zero net currents? Because it is going to take more sodium outside the cell and take lesser potassium into the cell, right? It is not like it is going to throw equivalent amount of sodium into and potassium outside the cell, right? Or vice versa. So this is what this circuit will look like when the sodium potassium current is also attached into this picture, right? So when we were talking about ion channels or the leakage channels, sodium was being taken inside and potassium was being taken outside the membrane. Now, there will be an active transport of the sodium and potassium ions against these concentration gradients, wherein potassium again will be taken inside the cell and sodium again will be taken outside the cell. And this will occur through the sodium potassium pump, which is represented like this, right? So let us also think about the difference between this channel and pump. One major difference is that channel is a conducting ions passively, right? It is not utilizing any other energy, right? But pumps are actively consuming energy, right? They are using ATP to transfer potassium into and sodium outside the cell, right? The travel through channels is also fast, right? Because it is always open, right? But in pumps, they have to get activated. They have to use ATP. At one time, one kind of ions can only flow in one direction. So that is why the transport is slower as compared to the channels. Also, the net current through the channels is not zero, right? As we have assumed in the last slide. Through the channels also, there will be a different, like the final outcome will not come to be zero, right? So the membrane potential in case of multiple ions is given by this more accurate equation, which is known as Boltzmann equation, right? So in this, it says that Vm or membrane potential is equals to RT by F, wherein R is gas constant, F is Faraday's constant, T is temperature, into natural log of Pk uh, uh, K plus outside plus PNA, Na plus outside plus PCl, Cl negative inside, right? Upon PK, K plus inside plus PNA, Na plus inside plus PCl, Cl negative outside. Right, so this is the negative ions. For the negative ions or the anions, it is inside upon outside the uh, concentration, and for the positive ions or the cations, it is outside upon inside, right? So this is the Goldman equation, right? It is also known as the Goldman-Hodgkin-Katz voltage or GHK equation. This can basically okay, we'll discuss that in a while. So Vm over here is the resting membrane potential, Px is the permeability of the ion X, and the unit of this Px is going to be m meter per second, right? Note that the units gets cancelled out in the GHK equation, right? So yeah. So for squid axon at rest, the PK is to PNA is to PCl value is going to be 1 is to 0.04 is to 0.45, right? So you can remember that, and you can consider that if we are saying that in some case, uh, we are just talking about PK value wherein PNA and PCl are almost negligible, right? So then what are we going to do? This condition does occur in some cells such as glial cells in the brain, and in that case these values can be negated out and it kind of looks like the Nernst equation. So through this, we can also say that the Nernst equation is actually a special case of the GHK equation, right? Then we can look at the action potential, right? So now we finally come at what is action potential. Till now we have understood what is equilibrium potential. How is that equilibrium potential calculated? The equilibrium potential is different for different ions. How different equilibrium potentials can determine what the membrane potential of a particular neuron is actually going to be, right? Now we will see what is an action potential, how it is going to be generated, how it is going to be transmitted, etc. Right? Okay, just a moment. Just give me a moment. I'll share my screen again. So we were talking about the action potential, right? Uh, we have briefly spoken about it when we were discussing the PYQs, right? So, as you can see in this first representation, the action potential looks like a very distinctive peak, right? If there are small currents that are given, or small depolarizing currents, or currents that will actually cause some positive currents that will lead to some positive value of this resting membrane potential, right? If some depolarizing current is given, there is some kind of potential that is achieved, but it goes down very slow, very fast. So it rises very slowly. It remains at that, around that peak only. It plateaus and it dies away, right? While in case of action potential, when a current equivalent to a particular threshold is given, then it can actually, even if it is not very huge as compared to the last one, it if it is uh, you know able to cross the threshold of this depolarization, it will actually cause an action potential, right? And we will see why this happens, right? Why this kind of a peak is seen, why these small currents could not generate an action potential, but this slightly higher current can actually generate an action potential, and we will look at all these things, right? So when we apply small pulses of current, we see small changes in the membrane potential like this. But if a larger positive current is applied, we see different type of response, right? An action potential which has a larger and rapid increase of membrane potential, and then there is a rapid fall. But what is basically determining these action potentials? Which that is what we are going to see, right? So one of the major determinants of action potential is the ion channels, and we are going to look at why. Right. So we know that what ion channels are by now. We know that, and we know that they can be in multiple phases, right? They can either be closed or they can be open, depending on whether they are letting the particular ions pass through or not. But we are going to look at these ion channels a little more in detail, right? So the ion channels are not simply holes in the membrane, right? But they are actually made up of proteins that line a water-filled pore that allows the ions to flow through, right? What is going to happen is that there are some properties of these ion channels, right? They conduct ions at a high speed, that is conduction of ions across these cell membranes at very rapid rates, up to 100 million ions per second, right? They can recognize and select specific ions such as potassium ions and sodium ions. So, potassium channel is 100 times more permeable to potassium than sodium, while potassium channel is 15 times more permeable to sodium than potassium, right? So it means that a particular type of channel has a specificity for a particular type of ion, right? Some ion channels open and close in response to specific electrical, chemical, or mechanical signals, right? We are going to look at some of these ion channel properties, right? So one, we said that they are very selective, right? So let us look at how they can actually be selective. So when we talk about sodium and potassium ions, we can see that the radius of the or the diameter of the sodium ion is smaller than the diameter of the potassium ion, right? So this could indicate that, yeah, maybe the ion channels for sodium might have a smaller pore size, and that is why they can let sodium pass, but they cannot let potassium pass through, right? But is that true? So the answer to that is no, that we'll be looking in the upcoming slide. So how does a channel allow potassium ion to pass through while not allowing sodium ion to pass through? Like, right? So this has something to do with their electronegativity, right? So we are saying that these ions are actually present in an aqueous medium, right? So now, because these ions are present in an aqueous medium, they have a lot of water molecules that surround them, right? Over here, red can depict the oxygen molecules and white can depict the hydrogen molecules, right? The oxygen atom is more electronegative as compared to the hydrogen atom, which basically makes it more partially electronegative, and it makes hydrogen as partially electropositive, right? And what happens is that by creating this partial positive and negative charge, the Na or K ions tend to attract these partially negative oxygen atoms because they're of their positive charge, right? So both K plus and Na plus are positively charged ions, and they will basically tend to attract the partially electronegative oxygen ions, right? So once this attraction takes place, as a result of that, sodium ion is never present in isolation, right? It is always surrounded by a bunch of water molecules. This results in increase in effective diameter of the whole molecule, and these bunch of water molecules is known as the hydration shell. Okay, the ion with the hydration shell has a much larger radius than the ion alone, right? So if we look at this, the smaller sodium ion, because of the more localized charge, attracts more water molecules and has a larger hydration shell than the potassium ion. Thus, sodium behaves as if it is larger than potassium, right? So this can actually explain how potassium ion channel would basically eliminate sodium, right? It will probably now have a smaller size so that the potassium ions will be able to pass and the sodium will not be able to pass, right? So this will explain how channel could select potassium ions over sodium ions based on the diameter of the pore, right? But does it explain how basically sodium ion channels are more specific for sodium than potassium, right? So that is a difficult question. How can we find answers for that is that we can basically first consider that yes, ion channels are not actually tubes, right? We know this. This is a fact that they are not rigid tubes. They have proteins that can interact with the surrounding molecules. The ion channel for sodium has a selectivity filter also, right? So let us look at this. So this is basically the ion channel for sodium, right? Over here you can see that the proteins that are made up of the proteins that are making up the ion channel are actually in turn made up of amino acids, right? And these amino acids have various kinds of side chains that are present. When the ions are passing, they are interacting with the side chains of these amino acids, right? Such as these side chains, and within these channels, right? At this point of selectivity filter, which is basically a narrow region, right? Typically, ion channels have a narrow region in the middle known as selectivity filter. In these narrow regions, hydration shells cannot completely pass through. Like intact, it cannot pass through. So what it does is that the water molecules are stripped off. And after stripping these molecules off, only the K plus or the Na plus ion remains, right? So these are stabilized. The removal is energetically unfavorable reaction, but it can take place because any plus or K plus atom can be stabilized by the interaction with negatively charged amino acids, right? So after this is done, the ion can pass through and it can regain its hydration shell. Right. So after it passes through, it can regain its hydration shell, and this interaction will depend on exact positioning of these various amino acids. Right. In the sodium atom, the positioning is such that the sodium can be fully stabilized. Right. But it is not going to fully stabilize the potassium ion. So it is going to be optimized for sodium ion stabilization, but not for potassium ion stabilization. So that is how it is going to select for sodium over potassium, right? Then there are some gated ion channels, right? Some ion channels may have two or more conformational states that are stable. The transition of a channel between these states is called gating, right? Such channels can be called as gated ion channels, right? Now, there can be different conformational changes in the ion channels, which will depend on its opening and closing of these ion channels, right? There could be conformational change in one or more region, which is going to look like this, right? Then there could be a general structural change that, for example, it looks like this, but there is a global structural change and it collapses like this, right? then there could be a physical blocking particle or entity that is present at the end of this channel so that it is blocking the movement of the ions into or outside, right? Then, if we talk about the types of channels, depending on the stimuli that control the opening and closing of these channels, then they can either be ligand gated, wherein one ligand can come and bind to the channel, and only upon binding of this ligand will it open. Right. The second could be voltage gated, wherein depending on what is a kind of membrane potential, it can change its conformation. Right. And the final one is the stretch or pressure gated or mechanical gated ion channels, in which, depending on touch sensation or some pressure or stress that is applied, the ion channels can open or close. Right. Now, under the influence of these regulators, channels enter one of these three following states, right? Either it can be closed but activable, that is, it can go in its resting place, wherein for now it is closed, but it can be activated. It can be open or active, right? Wherein there is currently flow of ions through these channels and it is active for now. And the third can be closed and non-activable or refractable. So sometimes what happens is that these ion channels go into a closed state, and for some time point or some period of time, they cannot be activated how much ever pressure or ligand or voltage difference is being given to them, right? They are just not able to activate themselves. And that is known as refractory channels, right? So how is this membrane potential actually recorded? So it is generally done using a patch recording, right? The patch clamp that we were looking at, that is the kind of recording that is used in this case to actually determine the potential. So in this case, you can see on the left, we have a diagrammatic illustration of what this technique looks like, wherein a small glass pipette is taken basically and acetylcholine is filled within it. Now, acetylcholine is the ligand for these acetylcholine receptors, right? So once it is applied on a patch of the membrane, hopefully that contains only one ion channel, right? And it will have a oscilloscope that is connected to it, which will basically give the reading of what is the kind of potential in that particular across that particular ion channel, right? And this on the right side is the actual image of this patch clamp technique, wherein this is the cell body. On the membrane only, there is this glass pipette that is coming, and it contains acetylcholine, and it will be attached, right? And this is how it will look like. So the oscilloscope reading will actually look like this. So it will either be in a closed state or an open state, right? There will be no intermediate steps that are present, as you can see. It will either be closed or open, right? And so the recordings of these patch clamp techniques or the patch recording of these ion channels look somewhat like this, wherein opening and closing of a single channel is a binary and probabilistic event. Right. So why are we calling it probabilistic? Because we don't know for sure whether that ion channel will open or not. Right. And the second is binary. That is, either it is opening or it is closing. It is not retaining any intermediate form, right? That is why we are calling it as binary. Next, what you can look at is the ensemble average, right? So if we take an average of multiple ion channels, right? Over there, we were recording from a single ion channel. If we take an average of multiple of ion channels, then the average of multiple channels can show smooth transitions or larger tip size, right? What does this indicate? It basically indicates that the multiple ion channels might be going off at different time points, right? Not all of them might be synchronized with respect to time, that all of them are opening and closing at the exact same time. They might, vary as to when they are opening at all. So there are two kinds of whole cell patch configurations that are generally performed. One is the cell attached one that we were studying about, which is basically used to take the recording of a single ion. And the second can be the whole cell patch configuration, wherein the primary process is the same, that that glass pipette is taken and it is attached to a part of the cell membrane. And after that, what happens is that negative pressure is applied so that a suction is created, due to which this membrane opens up from the place point that it is connected to that pipette, and the inside and outside of this neuron becomes continuous, right? So that is a whole cell recording. And when we are doing this whole cell recording, what we can also do is we can inject something into this neuron, such as a neurotransmitter or some dye, to look at the anatomy of these neurons, right? So there are some properties of these action potentials that we now know of as far as we have studied, right? So one is that it can only be attained after it reaches a certain threshold. Then it is an all or none phenomena. Either it is there or it is not there. It is not present in the middle, right? In that range, it is not present. It conducts the signal without decrement. I'm sorry, I'm very sleepy deprived. Yeah. So it conducts the signal without any decrement. And there is also a refractory period, right? This period, that after an action potential, for a while it will not be able to generate a new action potential. After a while, it can generate another action potential. So it goes through a refractory period, right? Wherein another action potential cannot be generated instantaneously. These properties cannot be explained with the passive membrane properties, and passive with the passive membrane properties, that is how the sodium and potassium are moving into and out of the membrane, only that cannot explain these properties, and that is why scientists have pondered upon this for a while, right? And the key observations of some of these scientists, including Hodgkin and Katz, who were part of the GHK equation, Goldman-Hodgkin-Katz equation, were that the amplitude of action potential is reduced if the extracellular sodium concentration is reduced. So it is actually directly proportional to the sodium concentration, right? Also, any influx may be responsible for rising phase of action potential, which is true because during action potential, the membrane potential is going to a positive value, which is closer to the nursed potential or equilibrium potential of the sodium, right? Also, they propose that depolarization above a threshold can increase sodium conductance such that it becomes more dominant than the potassium conductance. Thus, we move closer to ENA, right? This is what we said in the previous statements discussion also. Then they also found that the falling phase of action potential was caused by a later increase in potassium conductance, right? So once it falls, potassium will actually increase, right? So when we talk about action potentials, there are some questions that remain, that why do we have this particular shape of the action potential, and how exactly does the conductance change during the course of an action potential in a quantitative manner, right? So whatever discussion had been done by Hodgkin and Katz, it was basically in a qualitative way, right? Quantitatively, how can we say that conductance is changing during an action potential, right? So for this, we can look at the Hodgkin and Huxley's proposal, right, in a moment. So Hodgkin and Huxley basically proposed that the conductances could be a function of voltage. That is, a change in V or change in conductance, right? So would lead to a change in conductance. So it sees that if there is a depolarization, then more sodium channels will open up and there will be inward flow of sodium ions, and that will further lead to more depolarization, and this loop will go on. To study this, one would want to measure conductances which vary with time at different values of V or voltage, right? But a change in conductance leads to change in voltage, right? So that is the problem. So then how can we actually look at this, right? If we are looking at conductance, voltage is changing. So how to actually look at it. So the solution for this particular question was voltage clamp. And we've come to what voltage clamp is, right? So this again we have discussed that if we say that in a media that is similar to the extracellular media the within the organism, just a moment. Yeah. So, when we take an axon and we put it in a media that is similar or mimicking the extracellular medium that is present outside of the neurons, and we put a measuring electrode, right, in the axon of this neuron. We can attach an oscilloscope to take the reading of the membrane potential continuously. And what we can also do is that there can be a command potential that we set, right? So this is a voltage clamp. That means that we are going to set the voltage to a particular value, and then we are going to see what are the changes in current that are occurring, right? So this command potential will be the voltage that we are setting. So for example, for us, we are setting a command potential of plus 30 millivolt, right? So what will happen is this axon will actually read the membrane potential, say that in the beginning it is minus 65 millivolt, right? It will come and it will give this feedback to the amplifier, right? And if the command voltage that we have sent is plus 30 millivolt, right? So it will deduct this plus 30 from minus 65 and it will give this feedback to this uh, particular system wherein compensatory current will actually be passed, right? So we are saying that inside it is negative and outside it is actually positive. The amount of current that we want is actually positive. So this means we will give positive current inside so that there is more depolarization of the membrane and the membrane potential comes closer to the plus 30 that we have set, right? So that is how it is going to work, right? It is going to go to this feedback amplifier is going to understand what is the difference between the membrane potential and the command potential that is already present, and it is going to go and undergo or give a compensatory current, whether it is positive or negative depending on what is the kind of command potential that we want to attain, right? And this is what the system is going to look like, right? The ionic current is balanced out by the compensatory current, so V does not change, right? The measurement of compensatory current tells us the value of ionic current. So, since we are maintaining it at a particular voltage, the voltage will not change, right? Because the ionic current that is being maintained over here is being balanced out by the compensatory current that is being given over here. But actually, measuring of this compensatory current, how much more positive charge we have to give, how much more negative charge we have to take away, all this measurement will actually determine the value of the ionic current, right? So we can set the set voltage or command voltage potential over here is basically called as a command or the holding potential, right? Then this was the voltage clamp. There is a very similar experiment that is known as current clamp, which is a little different in one variable than the voltage clamp. In the current clamp, the current is controlled and the voltage is measured, while in the voltage clamp, voltage is controlled and current is measured. And the kind of questions that can be answered by current clamp is that how voltage varies in response to various inputs, while the kind of questions that can be answered with the help of voltage clamp is how conductances depend on voltage, right? So the voltage clamp can also be implemented using a single electrode for both recording V and passing current, right? Example within a patch recording. So we can not only you know uh, read a current, we can also pass the current within that. So this is the circuit for the same. There is a cytoplasmic and extracellular side of the membrane, both of which have capacitance or insulation between them, right? So that the current is not passing or leaking through it. Then there is resistance or conductance that is present and the equilibrium potential that is depicted over here, right? The membrane current can be divided into the capacitive current and the ionic current. The ionic current can further be divided into leakage currents such as the passive ion channels for chlorine, sodium and potassium, then voltage gated sodium currents and voltage gated potassium channels, right? So, yeah. So in the voltage clamp, the capacitive current is basically equal to zero, right? Except when the holding or command voltage is changed. The leakage current is constant for a given compound command voltage, right? So this again is a voltage clamp recording, which basically says that if there is a small depolarizing current that is given, assuming that no voltage gated conductance is actually working, right? Because the voltage has actually been clamped, then there will be a slight depolarization, and then there will be a slight repolarization, right? Because wherein IM over here will indicate the value of compensatory current injected in the cell, right? But once we consider the voltage gated conductances, then the picture becomes more complicated, right? It is not easy to figure out whether the observed current is through voltage gated sodium channels or voltage gated potassium channels. This is where some of the chemicals become very useful, right? So how will we rule out whether a particular conductance is more due to a sodium ions effect or potassium ions effect, right? How are we going to make that out? So the chemicals that are used in this case are, for example, some naturally occurring toxins, right? For example, one of the instances have been shown here wherein tetrodotoxin or TDS is a poison that is found in pufferfish and in some animals. What it does is it selectively inhibits or blocks the voltage gated sodium channels, right? And it is 1,000 times more poisonous than potassium cyanide, right? Because it is blocking the sodium channels, and that is one of the major, channels that is actually conducting the action potentials, and it is, transferring information from the neurons outside. So that is why it is very important. then there are other many natural poisons that function by blocking some aspect of the neural activity and therefore lead to muscle dysfunction or cardiac arrest or respiratory problems, etc. Right? So when we talk about that whether it is the sodium or the potassium currents, we can basically look at currents from the large depolarization, right? So when there is a large depolarization, there is an action potential that is formed, and then we receive such a peak, right? So there is a large capacitive current over here, right, which is going up. Then initially there is an inward current, which is hyperpolarization, and then an outward current, which is depolarization again, right? So as the leakage conductance is constant, the leakage current can be easily computed and subtracted, right? So we can actually easily understand what is going to be the leakage current over here by basically subtracting that from the conductance value. Then we can separate the voltage gated K plus and Na plus currents if we can block specific channels, right? For example, we saw the use of tetrodotoxin to specifically block the sodium channels, right? So there are other channel blockers also. So for potassium ion channel blockers, we use 4-aminopyridine or ammonium, tetrathylammonium, right? Or TEA, tetraethylammonium, sorry, or TEA, right? So the currents, when we look at this individual currents of potassium and sodium, this is what it looks like. So when we measure it in the presence of TA, we do not see potassium currents, but only sodium currents. And we can see that there is an instantaneous change in the membrane potential of sodium, but it comes back to normal also very quickly. In case of potassium, that we have studied in the presence of tetrodotoxin, which basically blocks the sodium channels, we have seen that there is a delayed increase in the sodium current, in the potassium ion current, but this delayed response goes on for a while, right? So if we repeat the same experiment for different volumes of command voltage and measure the voltage gated current, this is what it looks like. So at a very negative value, we can see that there might be no Na or K plus currents, right? At a higher positive value, however, there will be more K plus currents, but at a lower positive value or highly negative value, there will be more Na plus currents, and these are what it will look like at different, command voltages. So in all cases, we can see that the starting or resting voltage is minus 60, right? The command voltage is indicated on the left over here. So the conductances GNA and GK can be measured from INA and IK. INA will be GNA into VM minus ENA, right? So current of sodium will be equal to conductance of sodium into membrane potential minus equilibrium potential for sodium, and IK is equal to GK into VM minus EK, right? So this is what it will look like at different, membrane potentials or at different conductances. It will look like this. So in case of sodium, again, you can see that it is rising very quickly and going down very quickly. In case of potassium, it is rising slowly and it is staying steady for a while, right? For a much longer time. So both the conductances change with depolarization. Hence, the name is known as voltage gated. Note that there is a difference in the speed of change of sodium, right? So we can see that the change in sodium is coming much faster than the change that is coming in potassium, right? So the GNA and GK are functions of V, or Hodgkin and Huxley determine the exact dependence, right? If you depolarize a neuron and don't clamp the voltage, then V will change depending on GNA and GK. And Hodgkin and Huxley basically received a Nobel Prize for the description of these changes in the voltage in 1963, right? this is what they found out, and through these basic derivations, we can now see that the membrane potential or the action potential is a sum of the sodium conductance and the potassium conductance of these ion channels, right? Also, there is one characteristic or stark difference that you can see between sodium and potassium conductance is that sometimes okay, we will come to that. So, according to the Hodgkin and Huxley model in the action potential involves the following sequence of events, right? The depolarization of the membrane causes some sodium channels to open rapidly, thus increasing the conductance of the sodium channels. This current causes further depolarization, thereby opening more sodium channels, resulting in more inward current, right? Then the depolarization then limits the duration of the action potentials into two ways, right? One, it gradually inactivates the sodium channels and it opens with some delay the voltage gated potassium channels, as we can see over there in the previous one, right? Then consequently, the inward sodium current reduces, the outward potassium current increases, and that tends to hypopolarize the membrane, right? And it looks kind of like this. Now, there is after hyperpolarization, that is when the membrane potential is rising and it is coming down after that, it is going far below the point where it had actually started, right? So, this is actually known as after hyperpolarization. And why does this hyperpolarization take place is because the membrane potential, as we know, is determined by the balance between different ions, right? The Na plus ions try to take the membrane potential towards their equilibrium potential, while that is towards plus 55, and the K plus ions try to take the membrane potential towards their equilibrium potential, right? Now, what happens when this is being done is that during an action potential, the sodium conductance has increased, but then it also inactivated while K plus conductance increased a little later, but did not activate, right? Then sodium, the potassium channels are still open at this point, and therefore the potassium ions keep on going out, and the membrane keeps becoming more and more negative. Because we have additional conductance here, membrane potential will go towards the equilibrium potential of the potassium ions, right? But towards minus 75 millivolt, but not below that. Also, the voltage gated potassium ion channels gradually close, right? So, these voltage gated potassium ions will gradually close, but they will not be inactivated, unlike the voltage gated sodium channels, right? The membrane potential can then result to the baseline, that is around minus 65 millivolt, right? So, from after this, we can see that the action potential has a particular kind of threshold, right? Even a supra threshold stimulus or a stimulus that is much more powerful than the one that can give the action potential, even if that kind of a stimulus is brought in, the threshold, the action potential will remain the same, right? It will not change its size or amplitude, right? Then there are opposing factors that begin to act, right? Voltage gated sodium channels open, which try to further increase the membrane potential, and the leak channels try to decrease the potential. That is why action potential size depends on voltage gated channels and does not depend on the stimulus size. So the sodium channels are inactivated for some time after an action potential, right? So these are in the open state, and after a while they are inactivated. And once they are inactivated, what will happen is that it is not simply closed, but it is actually inactivated. Once it's inactivated, it is not possible for it to be activated, even if a much higher threshold of stimulus is actually given, right? So it goes into a refractory period. When we look at a voltage clamp, what is a refractory period? It is a period in which the same amount of voltage can also not produce an action potential, right? Either because it is in a phase where it is not supposed to actually produce, give the same kind of response. Why does this refractory period occur in the first place? Because, like we said, that after the action potential has taken place, and when it has gone into that hyperpolarization, there are the sodium ion channels that are still inactive, right? So they are not just resting, they are inactivated at that particular point. So as long as they are inactivated, they cannot really be activated, right? Once they cannot be activated, no amount of stimulus can generate an action potential. Right. So in current clamp, we can see that during the absolute refractory phase, whatever be the amount of current, it cannot generate an action potential. But during a relative refractory period, what happens is that a higher current can actually generate an action potential, right? The minimum stimulus required to elicit an action potential at this point will be different than the actual threshold, right? And but it will eventually return back to the normal threshold, right? After it has crossed the relative refractory period and after the inactivation portion of or phase of the sodium membranes are actually over, right? So the refractory period is the amount of time which is in a few milliseconds after a spike in which it is possible, in which it is impossible, that is absolutely refractory period or difficult in relative refractory period to get another spike. The reason for this is the inactivation of sodium voltage gated sodium channels, allowing closing of K plus channels, right? So how does the signal propagate along an action potential, right? And that too without deteriorating. So we had talked about this length constant and like how lambda is the distance at which the signal has basically deteriorated by around 63%, right? So how is this basically calculated, right? Uh, so I have prepared slides for this, but I think a significant number of them are actually left. So I'll pick it up in the next session. This one topic will be left, and I pick it up in the next session, from where we can actually begin to discuss synapses also. Right. So I will talk about where this, how this action potential is being generated in the axon hillock of the membrane and how it is being conducted in one direction. Why does it not come back? How is myelination helping, etc. Right. So this I'll take up in the following session. For now, I'll stop sharing my screen. Yeah. But I will share the material for this one along with the slides only. So you can access them once NPTEL provides access to you, right? I'll just stop the recording. And thank you guys for bearing with me. So I hope it helped you, especially the PYQs in the beginning.